We consider now another chain rule or related rates type problem, and this one being a little more concrete than the previous model from the chemistry ideal gas side. Here we're going to consider actually walking over a surface over time and ask the natural questions of how quickly are we moving in various directions. So here's the scenario. We're on a hillside, and the hillside is defined by the function, the height of the hillside is given by x times y squared. And we're going to talk about that in meters, and x and y are travel in kilometers. So perfectly reasonable to have the inputs and outputs be different units. Let's notice that from the beginning. We're going to walk along a straight path over time. How is that a straight path? Well, every time we take a step in x, we take 3 steps in y, and that leads to a straight line path eastwards and more northwards. In fact, we can sketch that out. If that wasn't clear, what we could do is do a quick little table of values. At time 0, we're at 0, 0. At time 1, we're at 1, 3, 1, 3. At time 2, we would be at 2 and 6. And that gives us very quickly the idea that we're traveling in a straight line through the origin and walking in this direction on a map. So again, this would be the map view looking down from above on the x and y plane. What we're interested in, though, is questions like, are we moving uphill or downhill at a particular moment? We have the surface over top of the xy plane, or we have contours or a surface on top of the map that is not visible yet. And we're going to try to tease out the rates of change as we go through that. Let's talk first about units to see how these things would be interpreted. And these derivative rules and the idea of identifying their units come straight from single variable calculus. Z is in meters. T is in, let's go back for a second here, T is measured in hours. Those are the natural units that we use to define x and y. So we've got hours there, and x is in kilometers. As soon as we have those units naturally defined, then we can talk about the units of the derivatives. The rate of change of z with respect to t is going to be in meters per hour. So if we're walking along the path, dz dt tells us how quickly we are moving up or downhill. And again, those units make sense if we visualize ourselves walking over a surface. What's the rate of change of my height over time? How quickly am I moving up this mountain or down this valley? dx dt. This is in kilometers per hour. Again, simply by the units of x and the units of t. What does it represent? Well, dx dt is the rate at which we move east, or west, I guess. That component of our motion, east or west, is the x variable, and we're asking how quickly we're moving in that direction. So the rate of change of x with respect to t. Last but not least, what would the partial derivative di-z di-x? Notice this is partial because z is a function of x and y, so we need a partial derivative here. That partial derivative is in meters per kilometer. And that might freak some people out. But again, if you think back to the model or the application we're talking about here, we're asking for each kilometer traveled in the east-west direction, how much height do we gain or lose? How quickly do we move up or down? And it's very natural in this particular kind of environment to talk about kilometers in terms of map distances, but we don't usually have kilometers up and down. It's much more natural to use a smaller unit like meters to talk about the elevation and say we've moved up 100 meters when we drove this trip or we walked along this path. So this is meters of upwards of up-down distance per kilometer of east-west distance. That's another way to interpret that partial derivative. We'd also have another partial derivative of meters of up-down distance per kilometer of of north-south travel. So that would be our second partial derivative. So all of these things have a meaning. They can be interpreted, and I would encourage you to try to interpret them whenever there's any kind of application or context around the variables, because it also makes the calculations work out more easily too if you can keep these associations and meanings in mind. All right, let's go about the actual calculations. We are given the same functions again, and we're asked how quickly are we moving up or downhill 1 hour into the hike, so t equals 1. So this, how quickly are we moving up or downhill, the immediate interpretation of that is the partial derivative of z with respect to time. And what we're going to use then is a quick diagram again, where time is changing. As time changes, x changes. As time changes, y changes independently of x. But both x and y are required, x and y are both required to figure out what z is. So we can immediately write down our partial derivatives here. And I'm going to do some coloring to hopefully add some emphasis to the structure here. Oops. The first ones here are always partial derivatives because z has 2 input variables. The second ones are regular derivatives because x and y only have 1 input, 1 variable coming in, and that's time. So there's only a single derivative or a full derivative. There we go. So the total rate of change of z, of my height over time, as I'm walking along this path, I'm moving up or downhill at some rate of meters per hour. It can be computed by calculating the partial derivative of z with respect to the x travel, and then asking, well, how quickly am I moving in the x direction? And likewise, there's going to be a contribution of height from the changing in the north-south direction, and we ask, well, how quickly over time am I changing in the north-south direction? And once again, we don't, this time, actually, sorry, not once again, this time we don't have any of these derivatives immediately. We have to calculate them from scratch. So let's do that. Di z di x is, well, there's our function. It's going to be y squared. Di z di y will be 2xy. Derivative of x with respect to time. Derivative of x with respect to time is just 1. Derivative of y with respect to time is going to be just 3. And we also want to do this at 1 hour. Now notice these derivatives don't have t in them, but I'm given the t value. But fortunately, time dictates what x and y are. So we immediately know that x is going to be 1 and that y is going to be equal to 3. So we're going to combine these guys with those values, and that means we can calculate all the partial derivatives that we need. Z with x is y squared is 3 squared, or 9. Going back to this, and the y derivative is 2xy, 2 times 1 times 3, that's 6. These values are already fixed. So last but not least, we have all the ingredients we need for our derivative of z with respect to time. And di z di x, 9. Di x di t, or dx dt, 1. Plus di z di y, 6. dy dt, 3. And that gives us 9 plus 18 is 27 meters per hour. So the idea being, if we were to walk for 1 hour, we would go up roughly, remember this is an instantaneous rate, but we would expect that after an hour we'd go up about 27 meters if we were following the path that we're talking about. Let's take a look at how that plays out in terms of the contour diagram. So we had our function here, our path rather, there we go. This is the point we're at t equals 1. And we're walking, we said we walk from 0, 0 to 1, 3, and so on to 2, 6. So we're going in this direction. That's the path. Here are the contours. So these are the heights of the surface. As we walk this way, we're passing through height 2, height 4, height 6. So at time 1, we're at approximately 7 meters. And then what's the slope? If, again, we're walking down this path at some speed, that's harder to represent in this diagram, but it's a fixed speed. And at the rate we're moving this way, we can see that we're moving uphill. And we can't see the 27 meters per hour from this diagram because we can't see how quickly we're moving along this path. But if we imagine moving from here to here, that's 1 hour. And then here to about here is another hour. Well, we're crossing at 1, 2, 3, if there's about 10 there, 20, 25, we'd be going up about 25 just counting contour lines and doing a crude, not derivative, but secant type estimate of our rate of motion up the hill. So that gives us some sense anyway that if I was counting contours and said if I started here and ended here, how far would I go up? Well, yeah, around 25, 27 sounds reasonable in the 1 hour, the distance I cover in that fixed amount of time. So hopefully that adds some pictorial perspective to this chain rule application. For the calculation side, the same rules that we saw in the pressure and volume application apply here. Some relationship between the variables, and that relationship dictates the form of the chain rule that we use to expand out the derivative we're interested in.